Thank you for your introduction. So this is a brief outline. After the introduction, I will explain the objective and motivation for this research. In the experimental part, I will explain the shear horizontal surface acoustic wave sensor device we use. And we put special emphasis on why we use plasticizers in our sensor coatings and how we select them. And then we'll come to the results and conclusions. So the background for this investigation is really groundwater monitoring for BTEX compounds, which are listed here. So they are found in crude oil and its refined products, and therefore are good indicators for fuel and oil spills. BTEX has significant hazard potential for human health, especially benzene, which is listed as carcinogenic. And therefore, the EPA, Environmental Protection Agency, has set the listed maximum, it's difficult to avoid the button, it has set these maximum contaminant levels for BTEX compounds in drinking water. And you can see, especially for benzene, this limit is relatively low, so that's quite challenging to achieve. Now there is many accidental releases from storage tanks, production sites, and facilities, and they contaminate underground water supplies. In fact, in the United States, there is as many as 560,000 underground storage tanks, mostly at gas stations. And the EPA is reporting between 6,000 and 7,000 leaks annually. So this is quite a major problem. And the way to deal with such leaks currently is depicted in these graphs here. So briefly, currently you still take samples on site, so you have to send personnel to the site. Then you pre-treat the samples, you transport them to an off-site laboratory, you analyze them, and finally you do data processing. But this approach takes regularly up to several weeks or even months. In addition, it can be unreliable because the sample can deteriorate during transport, and it is also costly and exposes personnel to potentially hazardous conditions. So there is a need to develop an on-site monitoring approach. So our approach is to use in-situ monitoring with a resonance sensor device, and our device is a shear horizontal surface acoustic wave sensor, and ultimately we want to use an array of these. And our sensor is for direct detection of the analytes in the liquid phase as opposed to headspace detection. And one important point is that for the signal processing we use two resonance sensor parameters. So one of them is the usual equilibrium frequency shift, and the other one is the response time constant, which is rarely used, but which is really characteristic for a particular analyte. So it greatly increases our selectivity for each BTEX compound. This also allows us to do real-time assessment of the situation. Now, to develop plasticizer polymer coatings for effective BTEX absorption, you have to take several goals in mind. Specifically, you want to achieve high sensitivity and low detection limits, especially for benzene. That is difficult. You want to reach down to ppb concentrations. You need good partial selectivity. So different analytes should yield distinguishable sensing characteristics. And with all of this, you want to achieve enhanced long-term stability because you want to deploy our sensor device in existing groundwater monitoring wells at gas stations, and they should stay there for ideally at least a few months. Now this is our experimental setup. So similar to a groundwater monitoring well, we place our sensor device and the samples inside a closed measurement chamber. So the analyzed sample contains the BTEX, and the reference sample has been filtered to strip it of the BTEX compounds. And the three-way valve is selected such that we can switch between those samples without interrupting the sample flow. This is important to keep an undistorted baseline. That's important in turn for the response time constant evaluation. And currently in the laboratory, we still use a network analyzer to collect the data. However, the final goal will be to develop a portable system, and then this will be replaced with a phase and amplitude detector. Now, this is a brief cross-sectional schematic of the sensor device. So you can see that we use lithium tantalate as the piezoelectric substrate because it supports a free horizontal surface acoustic wave for efficient operation in liquid environment. As you can see, even the transducers can be exposed to the aqueous sample. You need at least one polymer coating, the selective polymer layer, for absorbing the analyte, and optionally you can add a second polymer underneath to improve the acoustic waveguide characteristics of the polymer. In most of our investigations we did not do that. Now, the transducers use a multi-electrode design to minimize phase distortion, and we found that this also minimizes the noise in our baseline. So here you can see a photograph of the sensor device we used for this investigation. So you can see we use a dual delay line design, so we can make a reference measurement. And I'm not showing it here, but we also developed a smaller device than this. Now, there's many investigations on this, but most investigations just use commercially available polymer coatings, most of which have relatively low partition coefficients for BTEX in water. Especially that's true for benzene, because unfortunately among the BTEX compounds, benzene has the highest solubility in water, so the lowest tendency to go into the polymer. This makes it challenging to achieve high sensitivity and chemical selectivity for benzene in polymer-coated sensor arrays. So the goal here for this investigation is to improve the situation by adding plasticizer, which for some polymers can greatly improve the coating performance. So you can even add plasticizer to a glassy polymer, which usually does not absorb analyte. It will greatly enhance the absorption characteristics for BTEX compounds. And also this way we can increase the number of polymers that are available for BTEX absorption for the ultimate application of a sensor array. Now, specifically, the effect of adding plasticizer to a polymer is to reduce the glass transition temperature, which controls whether the device or whether the polymer coating is glassy or rubbery at ambient temperatures. So the plasticizer increases the flexibility of the polymer, but on a molecular basis it increases the chain mobility and also increases the free volume in the polymer. And this leads to enhanced absorption of BTEX analytes, but also to accelerated absorption. Now, by varying the type of plasticizer and also the polymer-plasticizer mixing ratio, we can then tune the coating absorption characteristics, which gives us more control over the coating. And ultimately, it even opens up the possibility of designing entire sensor arrays from a single pair of polymer and plasticizer. Now, the selection criteria are as follows. We select usually glassy polymers because empirically we found that that gives us more control over the coating, because in that case we can add more plasticizer to the polymer. The plasticizer needs to have low volatility, and for aqueous phase application it needs to have low solubility in water. So usually we end up with plasticizers which have long hydrocarbon chains and which have a chemical structure which has a relatively low polarity. And the plasticizer should not adversely affect water quality, which means it should not be too poisonous, or well, it should not leach from the polymer in large quantities, especially for deployment in groundwater. And the plasticizer needs to be compatible with the polymer, so we need to look into polarity, or more specifically into Hildebrand and Hansen solubility parameters, which allow us to quantify the miscibility of the polymer and plasticizer. And we need to look into structural configuration and the size of the plasticizer molecule. So for this work, we ended up with the plasticizer diisoctyl acylate, or DIOA, and the polymer polystyrene. They were selected because they have similar Hildebrand solubility parameters as the analytes we are using, so you can see all these parameters are in the same range. And our polymer was selected because it contains a phenyl ring, and we found it has a relatively high affinity to aromatic analytes because they also have a benzene ring. And we collected a number of data for different sensor coatings. This is just one example. So this shows sensor response to different concentrations of benzene using a polymer plasticizer coating, which was 1.25 micrometer thick, and the mixing ratio plasticizer to polymer was 17.5%. You can see that it was exposed to different concentrations between 95 and 990 ppb of benzene. And these concentrations were independently measured using a GCPID, or that's a gas chromatograph for deionization detector. So you can see that around 100 ppb of benzene can easily be detected, which is not so easy in aqueous phase using polymer-coated sensor devices. You can also see that the frequency shift is linear with benzene concentration within the investigated concentration range, which is below a few ppm usually, and also within the instrumental error. So with the GCPID, you usually get an error in the concentration of ±5 to 10%. Now, another important aspect of the measurement is the long-term stability of the coating. So this shows the repeatability in a long-term experiment. In this case, the coating was 1 micrometer thick, and the mixing ratio was 17%. And the frequency shifts were normalized to 1 ppm benzene within the instrumental error. So you can see that from day to day, there is no systematic trend in sensitivity. So there is just a random scatter, which is probably due to the variation in the actual analyte concentration. Otherwise, the sensor response in terms of response time and sensitivity is repeatable for over 1 month. And also shown in this inset is we recorded the device insertion loss measured to track changes in the viscoelastic properties of the coating. And this inset demonstrates that the coating is physically stable throughout the measurement. And well, after day 36, we noticed that the sensitivity seems to slowly start drifting. So this device is stable for a little bit over 5 weeks. Now here are several plasticizer polymer coatings, and they are compared to various commercially available polymers. So we look into a number of commercially available polymers. So these are the 3 best we found. This is PEA, polyethyl acrylate, which gave us a very high sensitivity, but unfortunately it's not stable over a long time, just about 1 week when in contact with water. And PEC is polyepichlorohydrin, that's relatively stable and sensitive. And PIP is polyisobutylene, so that's not very sensitive, but it is stable. That essentially leaves us with 1 good commercially available polymer, that's PEC. So you can see that the plasticizer polymer coatings gave us in part much higher sensitivities. And even this one is still relatively good. This mixing ratio 22.9%, thickness 0.7 micrometer. And this gave us stability for over 3 months. So we can see that compared to commercially available polymers, the polymer plasticizer coatings show higher sensitivity and are good additions to a sensor array. This is a graph showing the partial selectivity for several polymer coatings. So again, you see the same 3 commercially available polymer coatings. And this is one of the polymer plasticizer blends. Note that in this case, sensitivity has been normalized to the analyte solubility in water and the molecular weight of the analyte. And for each polymer, the 4 values for the 4 BTEX compounds have been normalized to that of benzene. So you can see selectivity is relatively limited, so that's why we use the response time constant in addition to a frequency change. But you can already see that the polymer plasticizer blend after normalization gives us higher sensitivity to ethyl benzene and xylene compared to all the commercially available coatings. So it does make some contribution to the overall selectivity of a sensor array. In conclusion, we have shown that polymer plasticizer blends can be used to create highly sensitive coatings for BTEX detection directly in the liquid phase. Adding the plasticizer reduces the glass transition temperature of the polymer, turning even glassy polymers such as polystyrene in this case into chemically highly sensitive coatings. The plasticizer type has been selected to achieve maximum sensitivity and selectivity for a given class of analytes, and we can do that by still taking into account coating stability in the long run. By varying polymer plasticizer ratio, you can turn a single pair of polymer and plasticizer to create different coatings for a sensor array. So specifically, in our case, using 1 single pair of plasticizer polymer, we observed the highest sensitivity and lowest detection limit for our coating, there was 1.25 micrometer thick and mixing ratio was 17.5%. That the detection limit has actually been measured, so we made many measurements below 100 ppb concentration for benzene. And by increasing the mixing ratio and decreasing the thickness, we slightly lose some of sensitivity, but we get a stability for more than 100 days. In future work, we'll look into further stability studies with various polymer-plasticizer mixings to increase stability to more than 100 days. And finally, I would like to acknowledge the contributions of Rachel Mola, Ravi Kolhatkar, Laura Allison, Tut Kumsen, and Kartik Sottavaliya, and thank you for your attention.